Hello and welcome to my presentation. Today we'll be talking about BERT sentiment analysis on Vertex AI using TFX, or in other words, how to train and deploy a heavy natural language processing model to the cloud like a professional. Two words about me. My name is Tomasz Maćkowiak. I work as a machine learning engineer at the D Labs. And on top of my machine learning experience, I have a decade of development experience. About my sponsor, we are an AI software development company. We do both external and internal projects, and we are hiring. So if you are interested, check out either our website or go to the virtual booth in the conference. How is today's presentation going to look like? First, I'm going to do an introduction. I'm going to tell you what are the motivations behind even making this talk. I'm going to set some goals that we want to achieve. Then I will talk about the tools that we will use to solve the problem that we select. Then we're going to proceed to the implementation phase. We will first implement a model, then we're going to implement a machine learning pipeline. Finally, we'll try to run this pipeline and the model. But first we'll have to package it, then we will run it locally, then we'll try to run it in the cloud, and we're going to see how the artifacts from such a run look like. Finally, we'll talk about monies and general conclusions. So first, let's talk about the motivations. Why even make a talk on this particular subject? If I was to ask a room full of data scientists how to create a valuable machine learning model, I'm likely to get back such answers as they will be probably discussing what kind of architecture to select for the model, what kind of fancy feature engineering to implement, what kind of hyperparameter tuning to do. Maybe they would like to implement something from some recent research papers. But to the business owner, this all is just cost, risk, delay, and no tangible business value. Because in real life, it's production or nothing. Stuff that doesn't get deployed to production doesn't bring business value. And we as data scientists, we are not great at delivering stuff to production. Why is that? In my personal opinion, there are two facets to this problem. The first one is us. We as data scientists, we are not coders at heart. We don't always follow the best engineering practices. The other thing is that we use tools like Jupyter notebooks that incorporate some amount of manual labor and are not that easy to deploy directly. And the other facet of the problem is that generally the field is heavy and problematic. Our models are big and computationally complex. You cannot just drop a machine learning model into a Flask application and hope for the best. Our models come with huge dependencies. If you include any kind of machine learning framework into your application, you are jumping from megabytes of dependencies to gigabytes of dependencies. And we also have a big problem with preprocessing. What I mean by that is our models are usually comprised of two entities. One is this preprocessing logic, and the other one is the model proper. The preprocessing is all the stuff that you do before you start training your model. So doing all kinds of normalizations, all kinds of one-hot encodings, every bit of feature engineering, that's preprocessing. And then you have the model that is doing the actual learning and then computations. And we usually have a big problem with where does the preprocessing fit? Is this part of the model? Is this part of the external application? We usually have problems deploying this preprocessing code. So generally, we need MLOps. MLOps is a set of good practices for deploying and maintaining machine learning objects and machine learning models. And we here at D Labs, we agree that the field needs standardization. So we started looking about, and we turned our gaze towards some open source libraries that could help us. And we decided that TensorFlow Extended looks very promising. So we started to look into that, but we found ourselves in a little bit of a niche. It turned out that there are not that many online materials on the subject. They are usually in form of notebooks or single file code bases that are presenting rather simple pipelines, and they sometimes contain not such great coding practices. So we had this idea that we will try to do a deep dive into TFX. We will try to solve a practical problem using the library, and we'll try to adhere to stricter engineering standards. And finally, we're going to publish the results. And we did that. There's a full 70 plus page article and open source code of a helper library that we developed and the pipeline available. You can read about it under this link. This leads to our company website. I'm going to be showing this link also at the very end of the presentation. And the presentation that I'm doing today is kind of a highlights, kind of a trailer of this full article. I will be presenting the best bits, but the full stuff you can find under this link. There's also a PDF download there, which I recommend. So we wanted to solve a practical problem. So we needed to select the problem first. So for the model, we figured out we're going to do something about supervised learning, and we chose the problem of text sentiment analysis. Why? First of all, it's a super intuitive problem. You get a text, and you need to decide whether it is positively emotionally charged or negatively emotionally charged. It's very easy to understand. It's very intuitive. It's a binary classification problem, so kind of a standard problem. And one other constraint that we wanted to introduce is try to use as many ready-made components as possible. For the dataset, we found this dataset of 50,000 IMDb movie reviews on Kaggle. The dataset is very simple. We just have two columns. One is the text of the review, and the other one is sentiment. And the sentiment is either positive or negative. So we selected the problem, we selected the dataset. So now we wanted to create an automated end-to-end machine learning pipeline for training such a model. What should this pipeline do? Well, first, of course, it should import the CSV, then do some basic exploratory data analysis. Then it should train and tune a high-quality natural language processing model. Finally, try to evaluate this candidate model against some set of metrics and compare it to a previous baseline model. And finally, deploy this model to the cloud as an endpoint. So at the end of this presentation, I'm hoping that you're going to learn two things. One is going to be how to build a sentiment analysis model in TensorFlow, and the other one will be how to build and run a TFX pipeline in the cloud. So let's get building. We just have one problem. We are very short on time, so I will have to omit some stuff from this presentation. Everything that I omit, you can find in a very comprehensive article, to which the link is going to be displayed also at the very end of the presentation. So let's first talk about the tools that we're going to use to solve our problem. The first tool is BERT. BERT is a natural language processing model developed by the researchers at Google. It was trained on a huge text corpus. It was trained on book corpus and on Wikipedia text. When it was published, it was state-of-the-art, and it supports many downstream tasks by a combination of transfer learning and fine-tuning, and it's very widely used in the industry. Why do we select BERT? Well, first of all, it's a very high-quality model. You can get very good results with it. Another property of it is that it provides us with a summary vector for each text we put into our BERT model, which is going to come in handy. Fine-tuning of BERT is optional. You can fine-tune it for the best results, but you can also skip the fine-tuning step to save on computational resources. And we're going to have a very easy time integrating this model with TensorFlow thanks to TF library. The main tool that we're going to use is, of course, TFX, otherwise known as TensorFlow Extended. It's part of the TensorFlow ecosystem, and it's a framework for creating end-to-end machine learning pipelines. It has many built-in components that you plug together, kind of like Lego bricks, to build your pipeline from bigger pieces. Why do we selected TFX? Well, first of all, you're supposed to be learning from the best, and Google is actually using this framework internally for their own machine learning models. It supports very complex functionalities out of the box. There are libraries connected to it: TensorFlow data validation, TensorFlow transform, TensorFlow model analysis, which provide you with quite amazing machine learning related functionalities. It has support for large data sets. Underneath the hood, TFX uses Apache Beam, so it can work on big data sets and can work in more of a streaming fashion. It's not your traditional load everything into memory and then do some stuff approach. And it's largely code-free. You need to write very little code. Most of the stuff with TFX is declarative. And the biggest selling point for me is that you can integrate pre-processing to be part of your model. You can, this is the part I was talking to you about in the motivations, that we have troubles where to put the pre-processing. With TFX, it's very easy to integrate the pre-processing into the model in one comprehensive artifact. While working with TFX, we found that there are some deficiencies or some things that could be improved. So we created this TFX helper library that we open sourced. It provides some things on top of TFX. First of all, it provides a unified interface for creating pipeline components. In TFX, you get a set of standard components, and then you get cloud-oriented components that are supposed to be easily interchangeable. But the pattern you see in most of the documentation is like on the slide, that you get an if you are supposed to be running the cloud, then select the cloud component. If you are running locally, then select the local component, and the parameters also differ. We very much didn't like that, so we provided a layer of abstraction so you don't have to do that. We also simplified the component configuration. Especially for those cloud-oriented components, you need to provide it with a definition of the job that it needs to do, and reading up on the structure of the job definition you need to provide it is a bit tedious. You need to read a bit of external documentation, so we made that much easier, and it's very easy to parameterize your pipeline. And we also allow something that TFX doesn't allow you to do by default. We allow resource customization per component. We want to deploy this, the pipeline, to Vertex AI, which is part of the Google Cloud Platform. It's a set of machine learning services, out of which the one that we are interested in are serverless machine learning pipelines. Why do we want to deploy to Vertex? Because of the serverless pipelines. We love serverless pipelines because if we go serverless, then we don't need to manage a Kubernetes cluster. We are data scientists. We don't like to create and maintain Kubernetes clusters. And with Vertex AI, we can do without this totally. When we submit our pipeline to be executed, the Vertex AI runtime is going to provision resources for us. Those resources are going to be allocated for as long as the pipeline runs. When it finishes, the resources are released and you stop paying for them, which is fair and very easy for us. We can just get to our training and training our models and don't have to care about all the DevOps related with it. So we know what we want to do. So let's get cracking. But there's a problem of a chicken and egg nature. Do you first implement a model or do you first implement a pipeline? Well, it's hard to say. I made an executive decision to start with the model. So first, let's talk about the model concept. The model that we're gonna create is a binary classification model. We want to use BERT as a summary generator for the text that we input, and we want to put a small neural network as a classifier on top of BERT. And how would this look like on conceptual level? Well, we get our input data from the dataset in CSV. We get two columns, the review and the sentiment, both as strings. First thing we're going to do is we're going to encode the target. So whenever we see the sentiment being positive, we're going to output 1. If we see negative, we're going to output 0. The next thing we need to do is do a little bit of text cleanup, because those reviews, they contain HTML entities, which we don't really care about. We're going to replace all of those with spaces. And the next step is using the BERT preprocessor. Now we need to stop here for a little bit longer. Machine learning models, usually, especially neural networks, they work with numbers. Everything needs to be represented as a number to be processed by a neural network. And text is rather not that much numbers, right? we need a way of transforming text into numbers. And the way it's usually done is you first do some kind of normalization, for example, lowercase or your text. Then you want to probably do tokenization, which is splitting the text into words. And this is usually a little bit more complex than just splitting a string on spaces. In this example, we have 3 spaces next to each other. We don't want to create some empty words in between. That's just the simplest case. And then when you have the text split into words, you want to encode those words somehow using some kind of dictionary for the use with your model. There are many ways to do that. There's bag of words, there's TF-IDFs, many others. With the BERT preprocessor, we don't have to implement any of that. We get the BERT preprocessor, we throw the raw text as an input, and we get back stuff that is already preprocessed. And the BERT preprocessor returns us 3 outputs. The first one is input word IDs, and this contains the IDs of each token, each word in BERT's internal dictionary. You can see that each word in the sentence got some ID. There are also some special tokens, a starting token, a separator token, and some padding tokens. The next output is input mask. It shows where the input is and which tokens are padding. So there's 1 wherever we have input and 0 where we have padding. And the last output is input type IDs. This shows us the index of the segment the token belongs to, because with BERT you can have 2 segments as input. For example, if you have question answering task, you provide both the question and the text as 1 single input to the BERT model. In our case, we just have 1 segment, so everything is marked as 0. Once we have the text transformed into those 3 vectors, we can feed this to the proper BERT model, which here is called the BERT encoder. This is the big transformer attention-based model that is rather heavy. And what this model is going to produce for us are a few outputs, but the one that we are interested in is called pooled output, because it contains a multi-dimensional summary vector for each text we gave as input. Then we will take this summary vector and run it through a simple neural network. The first step is going to be running it through a hidden layer of a neural network with ReLU activations, and finally running it through an output layer that is going to have just a single node, and we want the output to be in 0 to 1 range, so we choose sigmoid as an activation function. Once we have the prediction and we have the target from the training set, we can plug those 2 into binary cross entropy loss for the optimizer to optimize our model. So now that we know what we want to implement and roughly how it's supposed to work, let's start implementing. The implementation is going to consist of 4 parts. There's going to be pre-processing, model creation, training callback, and serving signature. Let's just be aware that the code listings are going to appear now and they're going to be rather longish, but there's just no way around it. We are starting with pre-processing, and this is how a pre-processing callback looks in TFX. It has a very simple interface. You get a dictionary of tensors and you need to return a dictionary of tensors. And you can use any kind of TensorFlow operations in here or TensorFlow transform operations. What we want to do is first we want to remove the HTML entities from our input. We use regular expressions to do this. Once we get the text cleaned up, we want to run it through the BERT preprocessor. And to load the preprocessor, we use TensorFlow Hub library. It's very easy to load the preprocessor. You just give it basically a URL of the data files for the preprocessor, and it's going to take care of downloading that, caching it on disk for subsequent uses. So it's just 1 line of code to load such a preprocessor, and then we can run the clean reviews through it, and we get back those encoder inputs. Those encoder inputs are 32-bit integers, which we have to cast to 64-bit integers, because in TFX, the preprocessing step is actually serializing to disk the pre-processed data. The transformed samples are serialized to disk in TF record format, and that format supports only 64-bit integers. That's why we need to do that. Then we are encoding the target. Whenever we see the sentiment being positive, we output 1, otherwise we input 0. And we return a dictionary of both the encoder inputs and the target label. Then we can proceed to the model creation. And this is very much Keras code. There's nothing here that will probably surprise you. We construct the inputs. The inputs are the same outputs we got from the BERT preprocessor with 64-bit integers, which we then have to cast back into 32-bit integers because that's what the BERT model expects. Then we can load the proper BERT model. We are also using TF Hub. It's still just one-line statement to do that, very easy. You can notice here that I'm passing trainable equals false parameter. That means that I don't want the BERT model to be fine-tuned. It's going to be kind of a frozen. So the gradients during the optimization step are not going to be propagating through the BERT model, which is going to save us a lot of computational time and power. Once we loaded the encoder, we can pass the encoder inputs through it, and we get back the outputs from the BERT encoder. From those, we select only the summary vector called pulled output. Then this summary vector we run through a hidden layer. Then we run the output of that through the output layer with a single node with sigmoid activation. We construct the Keras model out of this. We set binary cross entropy as loss. We can add a simple accuracy as metric because our dataset is actually perfectly balanced. Then we can proceed to model training. This is a TFX model training callback. It's also rather standard Keras or TensorFlow 2 way of doing things. Only that the parameters you're going to use are all wrapped in this function arguments parameter. First thing we want to do in this callback is load the pre-processing logic that we created in the previous step. We load this from the function arguments. We can also load the schema of the transformed samples. Then we can prepare the data sets. Loading data sets, which I'm not showing here, is using TensorFlow dataset API just with a little bit of TFX wrappers around it. In the next step, we will load the best set of hyperparameters found by the tuner component. Then we build the model using the callback that we just saw from those best hyperparameters. We can also configure some callbacks, for example, a TensorBoard callback, so that we can view in real time how the model is training. We can also configure early stopping. Here I'm showing how you can extract custom configuration in the training callback. Finally, we do a very classic Keras model fit call where we give the data sets, the amount of epochs that we want to train on, and all the callbacks. This is pretty standard. And the next step is a little bit less standard. This is something specific to TFX. We loaded our pre-processing callback that we created in the pre-processing step, and we want to include this as part of the model. And we need to assign this as an attribute on the model instance so that when we actually save the model, the pre-processing layer is going to be saved with it. Then finally, we save this model to a directory that TFX points us to with additional serving signatures. And we're going to talk about those serving signatures right now. What are those serving signatures? The best metaphor is they are endpoints for the model. They enable us to provide custom logic on top of the model. So imagine that we are doing the sentiment analysis problem, right? What is the easiest API that we can give to end users to use our model? Well, the easiest would be if we were able to provide a flat list of texts and we would get back a flat list of predictions. But that is not how the machine learning model works inside. Even if we have just a single node output layer from a neural network, we're still going to get back a two-dimensional result from the neural network. Just the second dimension is going to have only one column. We can use the serving signatures to hide those kinds of implementation details from the users, so that we can provide the best, the simplest API. So how do we implement such a serving signature? We need to create a function and decorate it with TF function decorator. We tell it that is a function that receives a flat array of strings. Those will be the plain text reviews, and we will be pre-processing those before passing them further on. And this is how we can actually approach it. We get as input those reviews as text. We first need to prepare them to be in the same format as we saw them in the data set. So we need to reshape them a little bit to create the same structure of input features. We run those input features through the pre-processing layer. We get back transformed features. Those transformed features we can plug into the model, get back the outputs, and those outputs we can then reshape, squeeze out the unneeded extra dimension, and return to the user. So great, we were able to build the model. You probably noticed that most of the operations were pretty much standard Keras operations. We were using ready-made components. All the stuff from TF Hub, it was super easy to use. And we achieved the integration of pre-processing into our model thanks to serving signatures. Now that we have the model implemented, we can start to create a pipeline that will take care of training and deploying such a model. First, let's talk about how this pipeline should work. What should it do? Well, first, it should load the CSV dataset. Then, of course, we wanted to split the training set into training, validation, and test sets. We want to generate some data statistics. We want to generate the schema of this data. We want to pre-process the data. Then we want to run some hyperparameter tuner. And then we want to train a candidate model. Once we have the candidate model, we want to compare it to the previous baseline model. But first, we need to find this previous model. Then we can evaluate the candidate model, and we want to bless the candidate model only if it exceeds some static set of metrics. For example, we can say that we want the model to have more than 70% accuracy, and it improves over the baseline model. This is a very unique thing to TFX. If you wanted to implement this comparison between the model you are just training and the previous best model, it's not that easy. It's not as simple as just fetching the values of metrics from the previous run. No, because you can have a different data set that you'll be evaluating. In TFX, it actually finds the previous best model, it loads this model, and compares the two models, the baseline and the candidate, using any kind of data set you want. And you can achieve this with 0 lines of your own code, purely declarative, which is a great feature. Finally, if the model was blessed, we want to push it to an endpoint on Google Cloud Platform. So let's see how a pipeline definition could look like. What is the pipeline definition? Well, the pipeline just needs to create a collection of TFX components, and the output from one component becomes input to another component, and this is how we connect the components together to form the pipeline. So this is a sample pipeline definition. You usually write it as a function that returns an iterable of components. If you are using our helper library, you probably want to give the pipeline helper as the first argument. All the arguments are actually free for you to choose. You can implement whatever you want. Usually you would find there a path to the input data, maybe the required accuracy threshold, maybe the proportions of training, validation, and evaluation sets, and so on. The first step in the pipeline would be ingesting the samples from the CSV file. and we're going to use the CSV example gen component. We just need to configure what proportions of the training samples go into each split: training, validation, and evaluation. Once we have that done, then we can compute some statistics over those data sets. And here you can see how you connect different TFX components together. The outputs from the example gen component become inputs to the statistics gen component. This is basically the pattern that TFX uses. Thanks to connecting the outputs to inputs, it is able to create a graph of connections between the relations and dependencies between components, which ultimately becomes the execution graph of the pipeline. In the next step, we will use schema gen component to generate the schema of our data. Our data set here is very simple, and TFX generates the data set schema perfectly in our case, so we don't need to do anything about it. If you have a more complex case, what you would usually do is first use the schema gen component to create kind of a base schema automatically. Then you adjust the schema by hand and use import schema gen component to import this customized schema into the pipeline. In the next step, we want to do the pre-processing, and we use that. And to do that, we use the transform component. We plug in the examples that we imported, the schema that was generated, and we give it a pre-processing function as an importable name. This is the function that we implemented a few steps back. We can also tell it that it should analyze the training and validation splits and transform all 3 splits of our data set. Then we can do the hyperparameter tuning, but I'm going to skip over that and proceed to training. We construct a trainer component. We use our pipeline helper to construct this. Thanks to this, the pipeline helper is going to choose the appropriate instance or appropriate class of the trainer, either the cloud-enabled trainer or the local trainer. We give it the run function, which is the training callback. This is the one that we also saw a few steps back in the model creation section of the presentation. We give it the transformed examples. We give it the transform graph that comes also from the transform component. We give it the schema, the best hyperparameters that were found by the hyperparameter tuner. We can tell it which splits of the data it's supposed to run on, and we can also provide it with some custom configuration if we need. This will train for us a candidate model, but we wanted to compare this candidate model to a previous baseline model. And to do that, we first need to find this baseline model. And to do that, we can use the resolver component, which is able to find for us the previous blessed model, so the previous one trained by the pipeline. And then we can start to configure the evaluation. First, we need to provide some kind of mechanical details about the model. What is the name of the signature it's supposed to use in evaluation? What is the label of the target in the data set? And some other configuration. We can also provide slicing specs. In our case, we are providing just the overall slicing spec, which means that the whole data set is going to be analyzed. But you can use this feature to calculate fairness metrics. Imagine that your data set would contain a feature like, for example, gender. You can provide here gender as a slicing spec, and what TFX is going to do is it's going to compute the metrics for each slice of the dataset based on the value of the gender metric, so that later on you can verify whether, for example, your model is not working better for men than it is working for women. This is a very nice feature. You can use it also just declaratively by specifying some configuration in here. We are not using this because our dataset is very simple. We don't actually have a column that we could splice on. Then we configure the metrics that we want to, that we require of the model. And this is, I think, the best part about TFX, because I can provide all of this stuff declaratively. I just configure here that I'm interested in binary accuracy, and I want this binary accuracy to exceed some static threshold. So, for example, I want the accuracy to be greater than 70%, but also I can configure the change threshold, which is saying that I want my model to be blessed only if it improves with a certain epsilon over the previous baseline model. And this is great and requires 0 lines of implementation from me. We can plug this configuration into the evaluator component. We feed it the examples. We tell it which split of the data set it should work on. We give it the candidate model and the baseline model and the configuration. And it's going to do the evaluation, and the model is either going to receive a blessing from the evaluator or not. And finally, the last step of the pipeline is the pusher component, which can push the model to a directory if you're running locally, or if you're running in the cloud, it's going to push it to an endpoint on Google Cloud Platform. And it's going to only push it if it received model blessing. So if we configured our evaluator to give a blessing only if we, for example, improve over the previous model, we can thus make certain that we never push a worse model to production than we already trained in the past. And once you configure your pipeline, you can kind of view it you can view how it's connecting all the components together. This is a visualization from Google Cloud Platform, from Vertex AI. You can see that the components are connected together always through artifacts, because you connect an output artifact as an input artifact to another component. So great, we were able to create our machine learning pipeline. We used declarative code. Most of the pipeline steps, we just described what we expect from the pipeline, but we didn't have to implement it. Most of the stuff is codeless. Very few components require callbacks. Those callbacks are required only in those components that it's impossible to provide some kind of configuration. For example, for the preprocessing, it can be super custom. Also, training and hyperparameter tuning, they require some custom handling. But most of the components don't require any code, any imperative code from us. Thanks to our TFX helper library, we were able to avoid any if statements in our pipeline as well. So once we have the pipeline, we will want to run it. And to run it, first we need to package it. And there's obviously just one solution nowadays for packaging your applications, and that is Docker. What we're going to do is we will base our custom Docker image on the open source TFX image, because like that we're going to get lots of libraries, machine learning libraries already included into the distribution. There's, of course, TensorFlow, there's Jupyter Notebooks inside, all kinds of other machine learning related libraries. It also has included the support for both CPUs and GPUs, so you don't have to care about installing CUDA into your image. And thanks to using Docker, we'll be able to have support for multi-module Python code. What I mean by that is that we will not have to keep all our callbacks as just a single file code basis. We will be able to split our code into as many modules that we want, which we'll be able to import from one another. We'll be able to use some external libraries like our TFX helper library easily. This will help us to maintain better engineering standards in our code. And finally, because we will package this as a Docker image, it will be easy to deploy to the cloud. This is how a sample Docker file could look like. We are basing the image on the official TFX image. We are installing some additional libraries that we need. We are copying into the image our pipeline code, the runners, which we're going to see in a second, and all the modeling code that we need. And that's basically it. So we have the application packaged. We can proceed to running it. We will run it first locally. How it's going to work locally. The inputs and outputs are going to be stored on disk. If you wanted and did some additional configuration, you can also make this work in the cloud. So you can have the inputs and outputs in Google Cloud Storage, for example. The metadata of the pipeline runs is going to be stored in a SQLite database. The model is going to be pushed to a directory when it gets blessed. And serving is not going to be part of the pipeline. We'll be able to serve our model through TensorFlow serving, but kind of outside of the pipeline in the local setup. So how to create a script to run our pipeline locally? Well, it's not that hard. We basically need to configure where the inputs and outputs are supposed to be. We create this instance of a pipeline helper using the local pipeline helper class. There we plug in the name of the pipeline and the directories we want it to operate on. Then we call our pipeline, giving it all the parameters that we deem are needed. And we use the pipeline helper to create and run the pipeline. Pretty simple. This pipeline is going to be running locally with something called the direct runner, which means that it's going to be running kind of inside the Python environment. This means that you can very easily debug such a pipeline. You can put breakpoints in your code. You are able to put logging statements. You can do any kind of debugging and profiling that you would usually do with a Python application. It's very nice and easy like that. We are able to run this, of course, using a Docker container. We spin up an instance of a Docker container using the image that we built. We probably want to supply it to mount there inside the container, the input directories and output directories, so that we can see what the pipeline produced. It's very simple. And if the pipeline proceeds successfully through the whole thing, we're going to get a directory with the pushed model, which is going to be the serialized model, the self-contained model. We can use TensorFlow serving, vanilla TensorFlow serving to serve this model. We spin up a container with TensorFlow serving. We just need to mount the directory with the pushed model into that container, and we are able to query our model using HTTP requests. We are providing a flat array of input texts, and we get back a flat array of predictions. And this is great. We were able to run our pipeline locally. The setup for local running was very easy. We just had to configure some directories. We were able to get no-code serving just using the vanilla TensorFlow serving. We didn't have to in any way embed it into a Flask application or write even a single line of code to spin up an instance of prediction server. And the model is self-contained, as you witnessed through the input and output formats. Thanks to the serving signatures, the preprocessing is integrated into the model. So we just throw raw text into the model and we get back the predictions. Very nice to work API that we have created. Once we run it locally and it works, we probably will want to run it in the cloud. This will require a bit more configuration on the cloud side. We'll need to engage a bit more cloud resources. Our Docker image will have to be stored in an artifact registry. The inputs and outputs we probably will want to store in cloud storage. The training and tuning are going to be executing as custom jobs on Vertex AI training. The model is going to end up as Vertex AI model. The endpoint is going to end up as Vertex AI endpoint. And metadata is going to be stored in Vertex AI metadata service. How do we go about creating a runner for this? It's also not much harder, just that we need to provide a little bit more configuration. When the pipeline is running in the cloud, each component requests a new machine that it runs on. And those machines, by default, get assigned some standard machine type with set resources. By default in TFX, you are unable to customize those resources. But if you use our TFX helper library, you can actually do that. You can customize the resources per component. And we, for example, want to get a bigger machine for evaluator component because we have heavy BERT model. And when we are doing the evaluation, we will actually need to load two of those models, the previous baseline model and the current candidate model at the same time. So we need more memory. And we can do that using the resource overrides. We also can provide minimal resources to all the components that are themselves not doing any heavy lifting, that are just starting some other Google Cloud services. This is to optimize the costs on the cloud. Then we need to configure the Vertex AI pipeline helper. Here we provided with all kinds of cloud configurations, the name of your cloud project, the region it should work in, where the Docker image is, what service account to use, and so on and so on. Please notice towards the end that it's very easy to specify the machine types for both the serving and training. Also super easy to turn on GPU. Here in our example, we assign Tesla T4 GPUs to those training and serving machines. Then we run our pipeline creation function and use the pipeline helper to create and run the pipeline. Please notice that there's a parameter called enable cache. This is a function, a very nice function of TFX. It allows you to very easily cache your pipeline executions. If you activate this and TFX sees that the inputs to a component didn't change from the previous run of the pipeline, it will skip execution of a particular pipeline step and is going to use the results from the previous execution. So you can get a very nice caching mechanism basically for free. Once we created this runner, we can spin up a Docker container and schedule a run of such a pipeline. You just need to provide some credentials into the container because we need to authenticate with the cloud environment. And if you manage to submit it, you're going to be greeted with this kind of interface inside Vertex AI on Google Cloud Platform. This visualizes the pipeline, all the artifacts in it. You can view the details of the pipeline, the details of the components, how long they were executing, what is the status of their execution. You can track if this component already ran or it's scheduled. You can see if something goes wrong. You can view logs of all the components so that you can check, for example, what went wrong. And once your pipeline successfully proceeds to the very end, you are going to deploy your model to an endpoint on Google Cloud. Later on, you are able to query this endpoint using the same format of data, flat array of text, and you get back a flat array of predictions with some additional metadata there. It's not important. So we were able to run our pipeline in the cloud with absolutely no changes to the pipeline definition. Still, we get no code serving. The serving on Google Cloud, those endpoints, they're actually using TensorFlow serving underneath the hood. So it's the same technology. And we can take advantage of cloud scaling very easily if we wanted to run our hyperparameter tuning on multiple machines at the same time to speed up the search for the optimal ones. It's very easy. You just change one parameter and it's gonna the orchestrator is going to take care of communicating between, for example, 3 machines that are going to be dividing the work between them. Very neat. Finally, when you get to the end of the pipeline that it runs successfully, you probably will want to view the artifacts of the pipeline run. Sadly, we don't have time to show you how to view them. You can look it up in the full article, but I'm going to show how those visualizations look like. This is the output of the statistics generator component. Our dataset is pretty simple, so the visualizations here are also rather simple. This is the schema that was automatically generated by TFX. You can see that it figured out that the reviews and strings and sentiment are strings, and that the sentiment is an enumeration that just has negative and positive enumeration possibilities. You can use TensorBoard to track how your model is training in real time. You can view those training curves, the accuracy per epoch or loss per epoch as the model is training in real time. And this is the output of the evaluator component. This is kind of an interactive widget. If you had those fairness metrics configured, the slicing specs, you could view stuff divided by those different slicing slices of different features. In our case, it's a pretty simple visualizations. We can see that our model achieved over 80% binary accuracy. So let's talk monies. We did an experiment where we ran this pipeline without caching. We did 10 hyperparameter tuning trials on 2 concurrent machines with Tesla T4 GPUs. Then we had the final training done also on a machine with T4 GPU. We were running in the Netherlands region, and the whole pipeline was executing for about 8.5 hours, and it costs a little bit over 6.5 euros to execute. So that's not a bad price, in my opinion. Let's talk final conclusions. First of all, I would recommend you to not reinvent the wheel. If you have any kind of NLP needs in your project, use BERT, because it's a very good model and very easy to work with. We, with the whole of our heart, recommend TFX. We believe that is a good tool that can help you standardize your machine learning pipelines. We love the fact that thanks to TFX, preprocessing becomes part of the model. We love the fact that this enables us to have no-code deployments. We very much love the serverless pipelines on Vertex AI. They enable us to concentrate on actually writing the workflow, writing the pipeline. We don't have to care about provisioning resources at all. It's great. And if there is one thought that I would like to leave with you at the end of this presentation, is this: the process matters. You can have the best model ever created in your notebook, but if it's not deployed to production, it doesn't bring business value. And using TFX can help you master the process of deploying such models, and like that, you will be able to deliver business value to your clients in a more streamlined fashion. Thank you very much. I'll be taking questions now. Here is also, once again, the link to the full article. As I said, it contains the full information, all the bits that were skipped in this presentation, you can find under this link. Mogę użyć adresu URL, procesu wstępnego i adresu URL codera, wygenerować osadzenia słów i podać je jako dane wejściowe do sieci neuronowej. Tak, to jest dokładnie to, co my robiliśmy. Używaliśmy tego preprocesora do tego, żeby wygenerować te osadzenia słów. Te osadzenia słów zawierały ID-ki tych słów w tym wewnętrznym słowniku BERTA, więc ten preprocesor, którego my użyliśmy, i model BERTowy, którego potem używaliśmy w następnej fazie, one muszą się jakby ze sobą zgadzać, tak żeby ten słownik był wspólny między jedną a drugą częścią, więc tak, dokładnie to robiliśmy. Czy konieczne jest wstępne przetwarzanie tekstu za pomocą modelu NLP przy użyciu deep learning? Tutaj nie do końca jestem pewien, o co chodzi. Wstępne przetwarzanie tekstu można na różne sposoby zinterpretować. Można pomyśleć o tym, czy na przykład ten lowercasing jest wymagany. To zależy od modelu. BERT na przykład ma różne warianty swoich modeli. Są takie warianty, w których tekst jest przetwarzany właśnie zawsze lowercase, a są takie, w których case nadal jest utrzymywany, więc słowo this zapisane dużą literą pierwszą, a this wszystko małymi literami, to dostają dwa różne ID-ki. Czy można w jakiś inny sposób przetworzyć tekst, zanim się rzuci go na deep learning? No w jaki sposób trzeba to zrobić? Zazwyczaj to się robi właśnie w ten sposób, że robimy to na przykład lowercasing, jakąś transformację, musimy zrobić tokenizację i w jakiś sposób zaenkodować te słowa w postaci zrozumiałej dla maszyn. Tak jak wspominałem wcześniej, są na to różne techniki, są prostsze niż ten BERT preprocessor. Techniki takie jak bag of words, na przykład TF-IDF, to są techniki, które są prostsze, z nich też można skorzystać. Natomiast jeśli ja miałbym coś poradzić tak z własnego doświadczenia, to nie chciałbym nikomu rekomendować, żebyście to implementowali sami. Ja rekomenduję, żeby użyć tych gotowych narzędzi, takich jak na przykład ten BERT, gdzie to wszystko dzieje się samo i jesteśmy jakby pewni tej implementacji, bo jest sprawdzona przez tysiące innych użytkowników. Czy jest jakiś sposób na zmianę wyniku sentymentu BERTA z 1,5 na wartość zmienną między 0 a 1, podobnie jak na przykład wynik sentymentu Weidera, a może potrzebuję do tego innego modelu sentymentu BERTA? No więc tak, BERT, którego my tutaj użyliśmy, on był użyty jako generator embeddingów tekstu. My go wykorzystaliśmy do tego, żeby wygenerować podsumowanie każdego z tekstów, które daliśmy jako wejście. Więc ten BERT, on w ogóle nie jest przystosowany do tego, żeby robić analizę sentymentu. To jest ogólnie wytrenowany BERT, on był trenowany na takich zadaniach jak Masked Language Model, czyli zgadywanie, jakie słowo powinno pasować w zakryte miejsce, i Next Sentence Prediction, czyli czy dwa zdania sensownie mogą następować po sobie. My go wykorzystujemy do tego, żeby wygenerować te embeddingi naszego wejściowego tekstu, dlatego że on jest modelem bardzo fajnym i kontekstowym. On rozumie teksty dużo lepiej niż na przykład jeśli byśmy wykorzystali bag of words do tego, żeby przygotować ten tekst do sieci neuronowej, do dalszego przetwarzania. On analizuje kontekst tych tekstów dużo lepiej, znajduje powiązania między słowami w zdaniu, jest w stanie też rozróżnić rzeczy takich, z którymi na przykład NER by sobie nie poradził. My wykorzystywaliśmy ten model BERTowy przykładowo do tego, żeby zrobić intent detection and slot filling. Dla problemu logistycznego mieliśmy maile, w których były parametry wysyłek dla firm logistycznych i ktoś pisał na przykład, że chciałbym wysłać kontener z Szanghaju do Gdańska, i BERT jest modelem na tyle sprytnym, że właśnie bez takiego fine-tuningu jego byliśmy w stanie znaleźć i rozpoznać za pomocą tych embeddingów, które on generował, czy Gdańsk i Szanghaj, to w NER oba się pojawiały tylko jako miejsca. BERT był w stanie nam dostarczyć takie dane, które nam mówiły, że jedno z nich to jest miejsce źródłowe, a jedno to miejsce docelowe, więc ogólnie rzecz biorąc, BERT jest takim ogólnym modelem tutaj, generuje nam bardzo fajne kontekstowe embeddingi, a to, co my z nimi zrobimy potem, to już jest coś, co my chcemy dalej z tym zrobić. My tutaj stworzyliśmy sieć neuronową malutką nad tym BERTem, jako taka jakby nakładka na niego, i my tutaj zrobiliśmy właśnie 0 do 1, żeby nam zwracał. Moglibyśmy zrobić, żeby zwracał od 1 do 5, czemu nie? Także to, co my zrobimy z tym BERTem, to tylko nasza wyobraźnia nas ogranicza, można go wykorzystać do bardzo wielu zastosowań, dlatego tak jak mówiłem, on wspiera właśnie wiele downstream tasks, czyli można go dostosować do wielu różnych problemów. Ok, nie ma więcej pytań. Dziękuję bardzo i bawcie się dobrze na konferencji. Hej!